Today I am presenting our paper titled A Fog-Based IOV for Distributed Learning in Autonomous Vehicles. Let me first start with the scenario where this paper stands. As we are aware of, the Internet of Vehicles has had a lot of developments in the recent time, such that it is quite closer to the reality. The helping factors for all this development in Internet of Vehicles include the development in vehicular ad hoc network, vehicular delay tolerant networks, cloud computing, edge computing, and fog computing. So with this development of Internet of Vehicles, we can expect a lot of possibilities in terms of data and application services, especially for the connected vehicles and connected autonomous vehicles. These applications include safety, efficiency, and autonomy. On the other hand, there has been tremendous amount of research efforts in autonomous driving, so that it is also having its own strides. The major helping factor for the development of autonomous driving is the development in the artificial intelligence. We can expect this development of autonomous driving to help in alleviating various transportation management issues that include congestion, safety, and energy. There are still a lot of research efforts need to be put on autonomous driving for it to be a reality. Especially the inclusion of federated learning and incremental learning into the domain of autonomous driving can have significant importance. So with that scenario in mind, our paper, it is positioned in such a way that we are trying to integrate the federated learning for autonomous driving with the continuum of the fog of the vehicles, the edge network, and the cloud. So the idea is basically we want to enable continuous retraining of the federated learning models at the fog of the vehicles. At the same time, we want to utilize the edge network and the cloud to assist in aggregation of updates generated by individual vehicles in the fog of the vehicles. In terms of networking, we are aware of this fact that the major challenge for the development of federated learning in the current time is in terms of the networking, especially the host-centric networking architecture that is employed by IP networks at the present time has its drawbacks for the federated learning. For example, it's really uneasy to obtain addresses, especially in the dynamic scenario of vehicular mobility, and it is really difficult to maintain long-term and stable connections. As we are aware, it's the network topology is dynamic in our scenario, and then there is various overhead incurred by the routing protocols for the host-centric communication network. To this end, we believe the use of information-centric networking, especially name data networking, can have significant impact on the progress of federated learning. The basic ideas of name data networking is it is a pool-based networking concept, meaning any node that requires any data, it can send an interest packet to the network, and any entity in the network that has the data, it is not necessary for that node to be the producer of data. It can supply the initial consumer with the data. So with this kind of concept, it is possible to effectively use wireless broadcast channel, which in turn results in lower communication overhead. The basic idea for achieving all this is the use of data names for the communication instead of the IP addresses or any kind of addresses that is currently existing. So with the use of data names for communication, there is a natural support for the multicast, and also possibility of in-path caching. So any cache result can be utilized by any of the nodes in the network, since it is not directed for any fixed node in the network. So coming to the contribution of the paper, what we try to do in this paper is we try to extensively analyze the impact of mobility of the vehicles in that scenario we just discussed, in terms of the delay or the latency for the task involving federated learning in the vehicular fog. Why is it important for us to analyze the latency? Because it helps in understanding the feasibility of federated learning for vehicular environment. Since we focus on federated learning task over the fog continuum, we can assume the system to be useful in the real world. Also, we design a system for federated learning using the concept of name data networking. We extensively present the comparison results of using NDN versus IP in the scenario of federated learning in the continuum of the fog to the cloud. So let me briefly explain how the system actually operates. The vehicular fog to cloud continuum, it consists of CAVs, CVs, edge network, and the cloud. The CAVs and CVs are the vehicles in the fog, and the basic idea is CAVs, they hold, since these are autonomous vehicles, they hold the initial model, and then they are actually responsible for finding the workers that can update the model, and these workers are basically CVs. And CAVs, they send out interest to solicit these worker CVs. The CVs, they have both the environmental knowledge as well as the action taken by the drivers, and thus we have chosen them as the nodes for training the model. Once the training is completed in the CVs, these CVs send out interest to announce about the updates that they have created. The good part about this particular system is that multiple CAVs, who are the actual consumers of the updated models, can use the updates from the CVs. And finally, the CAVs, they forward the updates towards the edge servers, which in turn forward it to the cloud for the global aggregation, so that new improved autonomous driving model can be generated and sent out to the CAVs for next round of the training. Like I explained before, the edge network, it serves as the distribution center for the training model. So they host the initial model that they have received from the cloud. At the same time, they also receive the model updates that were sent by the CAVs after collecting it from the CAVs, and then they forward it to the cloud. And finally, the cloud server aggregates the model. The numerical analysis of our paper. We have identified two important tasks for federated learning in the scenario of fog to cloud continuum. The first is the worker solicitation, and the second is the update collection. With worker solicitation, we are interested in how the computation task from the CAVs can be distributed to the worker CVs. So for this, we allow multi-hop packet relays. And the important characteristics of worker solicitation is that it starts with the same initial model from every CAVs that are distributing the model to the worker CVs. Next is the update collection. And in update collection, we are interested in the analysis of how the training results from worker CVs be returned back to the CAVs. And since the update collection includes the updates, which are the most essential part of the overall system, so we allow communication only when the CAVs and CV encounter each other. And the interesting characteristic that is different from the worker solicitation is only a subset of CVs have the updates ready when the updates are being sent back to the CAVs. So let me go into the details of worker solicitation. So initially, the CAVs, they send out the interest for searching the worker CVs. We define the CVs that have received the interest and can participate in the training process as the holding vehicle. So in this scenario, the worker solicitation delay is the time needed for a CAV to encounter the holding vehicle. And it is very important to note that only a part of the vehicles, in fact only a part of the CVs are holding vehicles. Thus, for this kind of encounter to happen, multiple encounters should be required. And we are aware from the previous works that meeting of a pair of nodes in this kind of scenario, it follows a Poisson distribution. And the Poisson process can be defined by a parameter lambda. So the lambda is the it is how many times a pair of vehicles meet in a unit time. So for our analysis, we are using Markov chain. So like I said, there are n CAVs that initially have the model. So in each stage of the in each state of the Markov chain, we are having one more vehicles with the model. So when the node we defined as the holding worker, it has received the interest sent from any of these from any of these vehicles that have the model. When that interest is reached to the holding worker, that is when that particular state is defined as the absorbing state. So we can see that there are multiple trajectories possible for the interest to reach to the absorbing state, and the probability of a single trajectory is the combination of all the probabilities of the horizontal transitions in the trajectory, and the delay along a trajectory is the sum of delays at each state along the trajectory. And based on our analysis, we have found that the expectation of the delay, it decreases with the increasing number of CAVs that initially hold the model. We look at the numerical analysis of update collection. For the update collection, we allow time-bounded slotted time analysis. So the slot of the time is enough for a pair of vehicle to establish the connection as well as to transfer the data that is required. So it is important for us to keep this in mind that a CB, it will have updates available only when it initially had the model in the first place. And for our analysis, we are concerned with a single update collection. Thus, the process completes when a CAV encounters a CV with the updates. And in our analysis, we have considered the mobility history of the CAV encountering the non-participating CVs before it actually finds the one with the updates. And we have taken into the consideration of probability of this particular transition in the connectivity with the CVs. So to elaborate on the analysis part, we have used Markov chain analysis for the update collection analysis also. And the state space for this Markov chain analysis, it includes all the possible states of every CVs. So basically, a state of CV can be defined either as having updates or not having updates. And we generate a transition matrix of transitioning for connectivity of one CV to another. So what I mean by this is like a CAV, it keeps on encountering new CVs, and this particular connectivity between CAV and CVs, it keeps on transitioning. And when the CAV has transitioned to a CV with update, the model collection process is completed. So what we have found is this particular transition, it follows characteristics of terminative Markov chain. And through our analysis, we have found that the delay, it decreases with the increase in the probability of CVs having the model in the first place. I would like to discuss about the performance evaluation part of the paper. Through performance evaluation, we wanted to study if NDN's name-based routing and the inherent caching, if it brings any advantages over IP. In case of wireless channel uses, delay in model dispatch, and resiliency over mobility. And further, we also compare a pure fog-based NDN, which is the system that we propose in our paper, and hybrid edge fog NDN. So to explain the difference between these two different setups, in case of fog-based systems, the CAVs respond to the update collection interest sent by the CVs. And similarly, in the hybrid system, the edge servers respond back to this particular interests. So to present a sample result of the performance evaluation, as you can see in the figure, we have 5 different setups: IPCS1 and IPCS4. This is the hybrid model including IP. Similarly, NDN CS1, NDN CS4 are for the hybrid model using NDN, and NDN AV0.4 is the fog-based system proposed in the paper. And similarly, the CS1 and CS4, it means there is a single edge server present, and versus there are 4 edge servers present in that particular scenario. So to look at the delay of interest satisfaction in the performance evaluation, we can see that for single edge server, the IP-based scenario versus NDN-based scenario, they have somewhat comparable results. They are somewhat similar, although there is slight edge for the NDN-based system. This is because in case of single edge server, the result, we have not shown it here, you can find it more in the paper, is that a very few interests are satisfied because there is just one edge server responding back to this interest. And when 4 edge servers are present, the advantage of NDN becomes more pronounced. Whereas comparing the results against the fog-based system that we have presented in this paper, the average delay becomes drastically decreased with the fog-based system, and the delay for the fog-based system, it remains almost constant for any number of cars in the simulation. With that, I complete my presentation and I look forward to the questions.